Hey everyone, welcome back to this explainer. Today, we're unpacking the underlying mechanics of artificial intelligence to discover exactly how these systems achieve autonomous, open-ended learning. I mean, we constantly hear about AI learning from these massive datasets, right? But how do we actually build an intelligence that keeps learning forever, entirely on its own?
So let's just dive right into this massive question. Because honestly, solving this is the ultimate bottleneck for recursively self-improving systems. If we want true open-ended AI, we absolutely cannot have humans constantly in the loop filtering synthetic data or handcrafting curricula. The AI has to autonomously decide what is actually worth its computational effort.
To demystify this, we're going to follow a clear path. First, the open-ended AI problem. 2, what makes data interesting. 3, the shape of discovery. 4, predicting future aha moments. And finally, 5, testing the math in reality.
Starting off with Section 1, the open-ended AI problem, and specifically, the human bottleneck. This cycle perfectly illustrates the foundation of a self-improving system. Notice the alternating phases. We have a learning phase, where an algorithm, like gradient descent or reinforcement learning, extracts patterns to gain new skills. And then we have a generation phase, where the system uses those insights to create novel artifacts, like synthetic data or new tasks, all without any human intervention.
But, here's where things kind of break down. The crucial point is that without a rigorous mathematical criterion to filter the generated data, a naive system just fails. If large language models, for example, just iterate on their own output without a filter, they quickly degrade into pure noise. We call this model collapse. We desperately need a way for the AI to figure out which self-generated artifacts are actually useful to learn from.
Which brings us to Section 2. What makes data interesting? Let's define the criterion.
Historically, older methods basically just looked for data that surprised the model. But they failed, and they failed because they couldn't distinguish between two really vital concepts. On one side, we have epistemic uncertainty. This is the good stuff, uncertainty that holds learnable secrets and structural regularities. On the flip side, we have aleatoric uncertainty, which is just pure irreducible randomness.
If an AI just chases pure prediction error, it falls victim to what researchers literally call the noisy TV problem. Imagine an agent getting rewarded for finding things it can't predict. It might just end up staring at a TV screen showing random static. The static is entirely unpredictable, so the AI is constantly surprised, yet it's completely unlearnable. It yields absolutely zero progress.
So how do we solve this? Well, researchers defined interestingness as a heuristic for future compression progress. Think of learning as compression. When an AI understands a pattern, it can describe the data using fewer bits. True interestingness is predicting when new data will make describing the whole system mathematically simpler. It's really about finding that specific data, which once learned, actually shrinks the total encoding size of both the model itself and the data it processes.
Moving into Section 3, the shape of discovery. Let's visualize this learning. Take a look at the visual drops in these profiles. On the top, we have a complexity versus runtime profile, and on the bottom, a log size versus complexity profile. When the line goes flat, the AI is spending computational effort, but basically just memorizing. There's no real progress. But those sudden drops, those represent genuine compression breakthroughs. They are those sudden, effort-driven aha moments where the model fundamentally grasps a new underlying structure.
But here's the thing. We need to be predictive, not just look at the past. By looking at a partial profile, basically everything the AI has learned up to right now, we can measure the gap between the last observed drop and the current effort. This gap is known as the stagnation length. And it turns out we can mathematically use this exact gap to predict if another aha moment is coming. Which leads perfectly into Section 4, predicting future aha moments, the math of discovery.
Now, the math for predicting the future actually depends entirely on our prior assumptions about the universe of data the AI is operating in. The source research analyzes three massive priors over computable objects. The length prior assumes short strings are more likely, the algorithmic prior assumes objects generated by short programs are more likely, and the speed prior heavily penalizes long computation runtimes. These three priors radically alter just how optimistic an AI can be about its future discoveries.
But here it is. The absolute most important takeaway of this entire explainer is right here. No matter the exact setup, the expected future progress vanishes exponentially as the stagnation length increases. Put simply, The longer it has been since an AI's last breakthrough on a specific task, the exponentially less likely it is to find a new one. If an AI has been stuck on a problem for a long time without a drop in complexity, it is mathematically way better off just moving to a different, fresher problem.
There is a really fascinating nuance here, though. If we assume an algorithmic prior, which favors structure over just raw length, the model becomes wildly more optimistic. Compared to the baseline length prior, the algorithmic prior yields a quadratic increase in expected discovery. It essentially tells the AI, hey, if you found a deep underlying pattern recently, there's a very good chance another related pattern is just around the corner.
All right, Section 5, Testing the Math in Reality. Let's look at the empirical proof.
Researchers actually tested this on universal computational paradigms, starting with 2 tag systems. They ran 120 million programs, and reality perfectly mirrored the math. Notice how in these graphs, as the steps since the last progress increased, meaning the stagnation length grew along the x-axis, the remaining compression progress on the y-axis completely vanished. The empirical data perfectly traced that theoretical exponential decay.
And just to make absolutely sure this wasn't some kind of fluke, they tested it on an entirely different paradigm, running 2.3 billion complex programs in the brainfuck programming language. And the exact same exponential decay curve emerged. The longer the stagnation, the less likely the progress. This proves that this rule of inductive interestingness isn't just a quirky theory, it is universally embedded in computational physics itself. So, what does this actually mean for the future of artificial intelligence? Well, it entirely shifts how we must build open-ended systems. We have to program them not just to passively learn from whatever data we feed them, but to actively predict the shape of their own curiosity. They need an internal compass that measures their own stagnation length, so they instinctively know exactly when to abandon a boring data stream and pursue a fascinating one. I'm going to leave you with that final, kind of provocative thought. If an AI is armed with the perfect mathematical formula for interestingness, wandering the vast space of everything there is to know, what will it choose to discover next? Thanks so much for joining me on this explainer, and keep questioning the algorithms that are learning alongside us.